All right, folks, this is the practice for the points over points on roller coaster problems. Question 1, calculate his weight. I decided to make it easy and just have the same person going on all the rides. So his weight, his true weight, is the old school formula, W equals mg, so 74 times 9.8. Means the Earth is pulling him towards the Earth at about 725.2 newtons. All right, so we're going to use that over and over again in each question. Okay, location number 1, the top of the hill, and he is going, has a speed of 6 meters per second. Question A that you can't see says, draw a force diagram for Dennis at point A. So the Earth is always pulling him down, which is pointing towards the center of the circle. And we know that weight is 725.2. And he is touching a track, and the track is flexed, and so it reacts to that and pushes him up. So that is his force diagram. You're always going to have weight and normal. Question B says calculate the normal force. There is only radial columns, right? There's nothing left and right. So only radial means sum of the forces equals mv squared over r. In minus out equals mv squared over r. The weight is in. The weight, he wants to fly off tangent, and the weight pulls him down. So the weight is radial inward. The normal is actually pushing him radially outward, so that's negative. And we are looking for that normal force. So we already calculated the weight. Equals just his mass times his speed squared over the radius. Okay, and then that gives you, I'm going to move this over here, 725.5 minus n equals 313.4. We're looking for n. So I'm going to subtract 313.4 from both sides, and you get 411.8 minus n equals 0, which means n equals 411.8 newtons. Okay, and then, so remember that number, so that's B. And then C is how many G's is he feeling? So what I want you to understand conceptually is on Earth, you feel your weight. So 1 G for Dennis is 725.2 newtons. Okay, so think of this like a conversion. He feels 411.8 newtons. That's the pressure, that's the normal force. 725.2 newtons is equal to 1 G. And when you divide these, you get 0.568 G's. So a little over half. He's feeling half his weight. That should make sense because he's literally inertiaing himself off the track, so the normal is going to be less than his weight, so he feels lighter. That's why your stomach feels kind of goofy when you go over the top of the hill. Okay, so it's okay to have a fraction of a G, and it means you feel lighter instead of heavier. Okay, and then D, we're looking for speed to not fly off tangent. That means he's going to lose contact. That means the normal force equals 0. So the force diagram is the same, except this is now 0. So instead of weight minus normal, it's just the weight. There's one perfect speed for which that weight is exactly what it needs to be to turn him. If he goes faster than that, he's going to fly off tangent. If he goes slower than that, the weight isn't enough to turn him, and that's what triggers the normal force. Okay, so he's still going in a circle, but the fact that there's no normal means you only have the radially inward force of the weight. Okay, and then we know that the weight is 725.2 equals his mass times, this is what we're solving for now, v squared, and the radius is still 8.5. Okay, and then that turns into 725.2 equals 8.71 v squared. Divide both sides by 8.71, and you get v squared equals 83.3. Take the square root of both sides, and you get 9.12. So let's check our work. If he goes 9, he loses contact. So go back here, and he was only going 6, so that makes sense. The normal force was not 0 because he was going slower. So he's going slowly enough that the weight was more than it needed to be to turn, so the weight was actually, in addition to turning him, pushing him into the track, which caused the normal force. Okay, so that was analyzing Dennis at the top of the hill. Now we're going to analyze Dennis at the bottom of the hill. Okay, the Earth is still pulling on him with 725.5, but now the Earth still pulls down, but now that weight is radially outward. And he was headed this way, so he's literally slamming himself into the track, causing a normal force. Okay, but now the normal is inward, so the normal is positive and the weight is outward. Okay, so we drew the force diagram. And question B says, find the speed he should have to feel 3.7 Gs. So the first thing you have to do is translate what does 3.7 Gs mean. What that means is the normal is 3.7 times his regular weight. So it means the normal is 2,683 newtons. Okay, so now that we know that, we are ready to apply in, which is the normal force, minus out, which is the weight, equals mv squared over r. We know we want the normal to be 2683. We know his weight is 725.2, and that's going to equal 74 times what we don't know squared over the radius, which is 11. Nope, that's his speed. Over the radius, which is 12. Okay, so this is the normal force being 3.7 Gs. This is the weight, and that's his mv squared over a different r. He's at a different part of the ride. Okay, that yields 1957.8 equals 6.16 repeating v squared. Divide both sides by 6.16 repeating. And you get v squared equals 317.5. And then take the square root of both sides, and you get v equals 17.8 meters per second. Okay, so to feel almost 4 times his weight, he's got to go 17.8 meters per second. That's how hard he has to, that's how fast he has to slam himself into the track to create a very large normal. All right, last question, I believe. Now he's in a loop-de-loop with a different speed. So question A, draw the force diagram. So the Earth still likes him with 725 newtons, but he was trying to fly off tangent this way, slamming himself into the track, causing a normal that is down. So now both forces are pointing towards the center, so they're both radially inward. Okay, we have a different radius, and then we want to find his normal force. So the normal is in, and the weight is in. They are both helping him turn. And this time we're looking for the normal. Okay, so the normal plus his weight equals, when you multiply all that, you get 20, oops, nope. Sorry, I'm just checking to make sure I didn't copy question 3 on question 2. I think I'm okay. Okay, so you get normal plus that equals 2356. That 2356 is looking familiar. It was 2683. Okay. And then subtract 725.2 from both sides. And you get the normal equals 2356 minus 725.2, or 1631 newtons. Okay, and again, just more practice with how many G's, because it's maybe a little bit counterintuitive. So he feels 1631 newtons. And 1 G is equal to his regular weight. So the newtons cancel, and you get 2.25 G's. So he feels like 2 1/4 times his regular weight. So he's feeling heavier at that point. And then question D says determine the minimum speed he must have to not fall off. So I wanted to give you one more practice with not falling off, means N equals 0. So if he goes too fast, you see the orange velocity, he is going to, oh, sorry, no. If he goes too slowly, the weight is more than it needs to be, and it will overturn him, which means he's losing contact. So if he has lost contact, the normal force is 0, and only the weight is causing him to turn. The normal force doesn't exist anymore. So one more time, 725.2 equals 74 times, this is what we care about, over the radius, which is 3.8. So 725.2 equals 19.47 V squared. Divide both sides by 19.47. And you get V squared equals 37.24. Take the square root of both sides, and you get V is 6.10 meters per second. Okay, that is practice for roller coaster problems for the points over points. Thanks for listening, and I'll see you in class.